Hello everybody and welcome to this next video here from MathBoy, and we're going to be looking into the L further math specification, and we're going to be looking at first order differential equations. Now, I've put a video already by the time I filmed this on differential equations for A-level maths. Now, in A-level maths the differential equations are quite simple, okay? So in further maths we're going to step this up a little bit, because what you know already is that dy by dx will be just some function of x. You've met that lower down in A-level maths. Then we stretched it up a little bit using the technique of separation of variables. We've got f of x times a function of y. That way you use separation of variables technique. A first order differential equation, what we're going to be looking at, just has a dy by dx and some function which we usually call p of x of y, p of x times y, so you can probably guess what we're going to be using there already, which is going to be some other function which I'll call capital Q. Okay, a quick note on notation, dy by dx squared, not allowed, y squared, not allowed. You can't write those. Alright, a d2y by dx squared, you might think, okay, that's fine, but d2y by dx squared we usually write as y double prime. Likewise, just dy by dx we know is just y prime. You might see, so physicists that are watching this, you might know that dx by dt, as something changes in respect to time, you might write x dot, like so. You might write that, which is fine, but I don't really see it a lot. You might see it in exam papers, which is why I want to mention it. d2x by dt squared, for example, is another example, but as we've got two dots, as it's the second derivative, and obviously, as you can probably guess, dy by dt will just be y dot, like so. Okay. So this is an intro to differential equations, first order. I'm only going to do first order in this video, so we'll look at first order. We might need some modelling today as well, we'll see how far we get. But second order, so the ones with a d2y by dx squared in them, I'm going to do a separate video on that, okay? And we'll do modelling with those as well. And then we've got to do coupled differential equations, so basically solve them simultaneously. We'll do that as well in the other video, which I'll film after this. Okay, so that's what we'll be exploring in this video. Okay, so this is my introductory example to this video. We've got to solve e to the x dy by dx plus e to the x y equals 2x. Now, I don't think you'll need separation of variables on that. You'll be there for absolutely ages. But there is actually a clever technique that you know from differentiation, and you know about the product rule, don't you not? Well, the product rule said...
Just a quick reminder that you need most of your second year pure L maths before you can actually start this section. Alright, so let's go back right to the video.
That if you had y being a function of x times another function of x as well, you might have x squared log x, for example, then you would say that log being f prime of x times g of x plus f of x times g prime of x. That's our derivative. Okay, so that's the product rule. Now, how can we apply it to this? Well, what would our f of x and g of x be? Well, when we're solving this, what's the easiest thing to do? Well, the easiest thing to do is to say, well, that's just a derivative of e to the x y. Yeah? That's all that left hand side is. And that 2x can just stay the same. Now, how do I get rid of a dy by dx? So I've got a dx, d or dx in this case. Well, how do I get rid of that? Well, I just have to integrate both sides, don't I? So I want the integral of those two sides. Okay? Well, integrating a derivative just gives you itself, as we know. Integrating 2x, well, 2x will give you x squared plus some constant c. Rearrange to get y equals. So y equals, well, let's do 3 by e to the x, don't we? So we get x squared plus c over e to the x. And that would be the general solution to the differential equation. Okay, so we're using this technique that will basically develop in the next coming section. Okay, so we'll solve this one now. This is a bit of a development on the technique I just gave you. So we're going to solve sin x dy by dx plus y cosine x equals 3x squared. Okay, so first line of working would say, well, this is just the derivative of sine x times y, or y sine x, whatever you want to say, but sine of x times y will also be fine. And for that 3x squared to stay the same. Now to get rid of it, we just integrate both sides. Well, integrating the derivative just gives you itself. I will write it as y sine x just to make it easy when we basically scale this back down in a second. For x squared, well, that's just x cubed plus c. We can integrate those, pretty simple now. All we need to do then is just divide by sine x, and that will give us y equals x cubed plus c over sine x. And that is the general solution to the differential equation. Alright then, so we're going to solve this one. We're going to solve dy by dx plus 3y over x equals 4. Now you might think, what the hell is going on here? Now this will be a little bit of trial and error for you guys, because it's not in the form that we know about for the product rule. Now this is going to kind of be plucked out of thin air as such to where this is coming from, but that will be explained in a later part of this video. It's what we call the integrating factor. You'll probably see why it's called that when we get to it. But I'm actually going to multiply it by x cubed. See what happens. X cubed dy by dx. Now the plus, well, that's going to give me 3x squared y equals 4x cubed. Hang on. We've gone from a line that made no sense to us to something that we know about. Because we can solve this now. Because what's this? This is just the derivative of x cubed y. Yeah? See what I've done there? If you've not spotted it, it's completely fine, because I will introduce you to where this is coming from in the later part of this video. Okay? So, all I need to do then, integrate both sides. So we get x cubed y, just solving this now. 4x cubed, well, that will integrate to x to the 4, won't it? Plus our constant c of integration. Divide through by x cubed now. We get y being x to the 4 plus c over x cubed. Of which you could probably write that as x to the 4 over x cubed plus c over x cubed. That was giving me x plus c over x cubed. Simplifying that down. Okay. So that is how we can solve this differential equation. I'm going to explain to you where that came from in the next part of this video. Alright then, so this is the integrating factors now, what I'll explain about in a second. So, the idea with this is, if I wanted to solve dy by dx plus p of y equals q, okay, I could multiply by something r, so I'm going to call this r, for example. So I'm going to say that r, which is like that type of r, of dy by dx, but like the r cosine of alpha, r sine of alpha sort of thing, plus r times p of y. Now what's going to happen here? Well, the r times the q will happen over here as well. So this is just d on the x of r times p of y, or in this case just y. Yeah? Okay, so where on earth is this coming from? Well, the idea with this is that r is an integral of such, and it's a weird funny integral, because if we have that dr by dx was for example r times p, which is what we had, alright, the integral of that of 1 over r, so using separation of variables in respect to r, like that, would be equal to the integral of p dx, because p is just some number. Okay, so integrating that will just give me log of r, using our knowledge of 1 overs, will be the integral of p. How do I get r? You just e both sides using that little e to the power of, here we go, the integral of p dx. That is what we call the integrating factor. Okay, where r is a function of x as such. This is the integrating factor. Okay. So if we went ahead and solved this then, that we'd have r dy by dx, okay, plus dr by dx of y, just solving this as you would, is equal to, well, I just need to do it to the other side. I get r dy by dx plus rp of y, and I get that. I get dr y on dx, because those will just go bye-bye, will be equal to, make sure I put the y down there properly, rp of y. Now we know for a fact that y can't be 0, because if y was 0 you can't differentiate with something equal to 0. So we've got dr by dx will be equal to r of p. And then this is where we can link up to this, and therefore find our integral. Okay, so this will start this chain off. Okay, and then you get down to your integrating factor. Okay, this I would highly write in it. I would highly be like highlighting over it, you know, doing all your fancy stuff. If you're some ladies that like doing highlighting, this is one of the things in this section which is vital in solving these hard differential equations. Okay, so we'll be using this fact that I've just explained in order to solve differential equations like the one we've just solved. Alright then, so what I've basically explained to you is the integrating factor, which is quite useful. Now, I'm going to hop back to the example I just gave you a moment ago. The example I gave you earlier was this: dy by dx plus 3y over x equals 4. Okay? So now we need our integrating factor, don't we? R of x. Now, r of x would be e to the power of the integral of p of x. What is p of x in this case? Somebody help me out. On the other side of the screen, it will be 3 over x. What's that? And the q of x, if you're interested, will be equal to 4. Because it's this bit on this side, using our general form. Alright. So we've got e to the power of p of x, which is 3 over x dx. Okay? Well, I'll give you that. Will give me e to the 3 log x, yeah? Well, I can rewrite that as log of x cubed using your log laws. E and log next to each other, they don't like being next to each other, so they get cancelled out, so I just get x cubed. And then I could multiply 3 by x cubed, which is how I knew I could multiply 3 by x cubed, because I could spot it immediately. That's how good you'll get, really getting good at with these. So you multiply 3 by x cubed, as you did before, so we'll get x cubed dy by dx, well, this is a bit of a mess now, plus 3x squared y equals 4x cubed. And then you go ahead and solve it. I will solve it again just to show for completeness that this does work, of x cubed y. Alright, we'll be equal to 4x cubed. Integrate both sides as we did before, we get x cubed y. Will be equal to x to the 4 plus some constant c. So then we get y being x to the 4 plus c over x cubed, just rearranging that equation. Okay. So that is an example of using the integrating factor to solve that one that I did earlier on in the video. Alright then, so we'll solve this one, which is a bit more challenging. Right, what do we want to do? Well, we need to find our integrating factor once again. I will use a different colour this time. I'll use blue. I've got r, the e to the power of the integral. Now, what is my p of x? Be careful, my p of x will be 4 over x, alright, because you just divide through this. by x, get into our normal form, plus 4 over xy will be x to the minus 7 halves. Be careful, you have to change that as well if you divide through by x. Okay, so then I get e to the power of the integral, well p of x now is just 4 over x, because p of x times y, isn't it? 4 over x will give me e to the 4 log x. I can bring the power up to the top, so I get e to the log of x to the 4. E and log cancel out, x to the 4. Okay, and that's how quickly we can do these. Multiply through and now we get x to the 4 dy by dx. Now 4 over x to that will give me 4x cubed y, like so. Will be equal to now, multiplying by x to the 4, well x to the 4 will be 8 over 2, add minus 7 over 2 will just give me x to the half. Yeah? So then this is a perfect derivative, this is d on dx of x to the 4 times y will be x to the half. Okay, keeping with our stuff as we do. Integrate both sides, we get x to the 4y. Integrate x to the half will be 2/3 x to the 3 halves. Plus the constant c of integration. Then how do we finish this off? Well, I just need to divide through now. I get y is 2/3 x to the 3 halves plus c divided by x to the 4. Okay, just enough room to squeeze it on there on the board. Alright, that's how we can solve this more complicated differential equation. I've got one more for you. Ramping up the difficulty now, we've got dy by dx minus 2y equals e to the 10x. Integrating factor r will be equal to e to the power of the integral of minus 2 in respect to x. Well, minus 2, any number just getting an x, right? That'll be e to the minus 2x. So all I need to do is multiply through by e to the minus 2x. Multiply through by the integrating factor. Get e to the minus 2x, minus 2 times that will give me minus 2 e to the minus 2x of y. E to the minus 2x times e to the 10x, or take 2x away, will give me e to the 8x. Then all I need to do now is put that as a perfect derivative, of which it is. Perfect derivative, our lovely world of calculus, will be e to the minus 2xy. Because I've still got the y there. So that should be a dy by dx there. Try and squeeze it in. Okay, that. And obviously I've still got the e to the 8x on the right hand side as well. So we need to integrate both sides, will give us e to the minus 2xy. Now integrating e to the 8x, well, it'll be 1 over k e to the kx, so it'll be 1 over 8 e to the 8x plus the constant c. So I just need to multiply through by e to the 2x, or whichever you prefer, doesn't really matter, it'll give us 1/8 e to the 10x plus c to that. You could write that as a if you really wanted to, but c is also fine. And that will be the solution to this differential equation. Okay, so we'll look at some particular solution examples now, because you can still do particular solutions, it's just a different technique. So we've got the integrating factor then, well, nice and easy. That'll be e to the power of the integral, well that's 8. Not 8x yet, 8 dx. It gives e to the 8x. Okay? Finish, multiply through by e to the 8x, so I'll get e to the 8x dy by dx plus 8 times e to the x times y will be equal to 2e to the 8x. Looks pretty nasty, but it is a most definite perfect derivative. Integrate both sides, we'll get e to the 8xy. Integrate 2e to the 8x, well that'll be 2 over 8, which is a quarter. E to the 8x plus the constant c. So this is just got in terms of y now. Get our general solution, so that'll be 1/4, because I'm essentially multiplying through by e to the minus 8x as such. 1 plus c e to the minus 8x, you have to be careful there. Okay, so this will be our general solution to the differential equation. The particular solution is where it gets a little bit more tricky, because I need to sub into this in order to find what the value of c is, as such, using this information when y is 5/4 and x is minus log of 2. So I've got 5/4 will be equal to 1/4 plus c e to the minus 8 times negative log of 2. Okay, so, well, I can just take that away, that'll give me 4/4, which is just 1. Will be c e, now minus 8 to the minus log of 2. That's a log of, my word, what's that, 2 to the 8. That's 256. 2 to the power of 8. Yeah. So I need to just get c on its own now. Well, e to the log will just cancel each other out, so it'll just give us 1 being 256c. So I'll just end up with that c is 1/256. So the particular solution to this differential equation will be y equals 1/4 plus 1/256 e to the minus 8x. And that is the particular solution to the differential equation. Right, I'm going to solve this beast. We've got solve dy by dx plus 3y cot 3x is equal to 12 cosine 3x cot 3x, when y is root 2 and x is pi/12. Now, I don't fancy dealing with this using separation of variables, so of course we're going to use that new technique of the integrating factor. So r will be equal to e to the power of the integral of 3 cot 3x. Now, cot 3x is cosine over sine, isn't it? So it'll be e to the power of the integral of 3 cosine 3x over sine 3x. My word. So using the log trick, that'll be e to the log of sine 3x. My god. Look, I've got e to the log next to each other. That'll just give us sine of 3x. Okay. I do not fancy working out this in a mess, do I? So, solving this then. So, you multiply 3 by sine 3x. So I get sine of 3x times dy by dx plus, my word, I have to start my head up, 3y times cos so it's 3y times cosine of 3x, which will be 12, blimey, this would be cos squared 3x, my word. Right, so we get, it's a perfect derivative of, blimey, so it'll be y sine 3x. I told you it's going to be tough. It'll be 12 cosine squared 3x. Now, cosine squared 3x, we can't integrate cosine squared with the knowledge we've got. We're going to have to use our double angle formula knowledge. If you've not covered this yet, it's in the trigonometry and modelling pure year 2. So if you want to hop to that. So we need cosine of 2 theta, don't we? So cosine 2 theta, the rearranged formula is 2 cos squared theta minus 1. Well, using theta, it'll be 2 cos squared of 3x. Take away 1. So I'm going to have to get the cosine 3x. Oh my god. Ooh, I don't fancy doing this, to be honest. But what's going to have to be done, isn't it? Because this is essentially cosine 6x, isn't it? Because it's a 3x times a 2. So I can divide by 2, that'll be a good shout. So I get that cosine 3x will be equal to a half plus a half cosine 6x. Right. So I can multiply by 2. So I get, if I multiply by 2, or shall I multiply by 3? Well, I can only think of multiplying by 12, to be honest. Well, that's the only other way I can think of it. So I get the 12 cos squared 3x, multiplying a half by 12, you get 6. That'll be 6 cosine 6x. Okay, so on this side we have to integrate that. So we get that y sine of 3x. Well, now that we can replace with this integrated. So we get 6x plus. Now cosine will integrate to minus sine, but that'll cancel out anyway, will give us sine of 6x. Cosine integrates to sine, doesn't it? Plus the constant c of integration. Divide through, we get y is 6x plus sine of 6x plus c all over sine of 3x. Okay? And that is the general solution to this differential equation. Not done yet, because it wanted a particular point, didn't it? So we have to sub in root 2 is equal to, now it was pi on 12, right? Now pi over 12 of 6x will just give us pi on 2 plus, now sine of that, which will be 1 using the sine curve, and also just got a plus c there on top. Sine 3x, or sine lots of 3 pi on 12, which is a quarter pi, which was, so it'd be 1 over root 2 1, wouldn't it? So I get to that. So I can multiply by the root 2 times root 2, so we get what? 1. It's 1. Not 1 plus, it's 1 equals, you bloody donkey. So this is what you get when you're doing so much differential equation and stuff. Get that, right? So we get 0 equals pi over 2 plus c. So c is minus pi on 2. Sorry, that is at the edge of the board. Apologies. So the particular solution to this differential equation will be y equals 6x plus sine of 6x minus pi on 2 all over sine of 3x. And that is the particular solution to this differential equation. Alright. So I did want to include model in this video, but I think it will be quite long, so I'll separate modeling out. Alright. So I'll end this one here, I think. And we can see you in the next video.